let's move on to our next topic, the next chapter. It's on orthogonal complements and orthogonal projections actually. So the next discussion that we're going to have is going to be on what we call so-called orthogonal complements. Now consider a vector, okay, so consider a vector in a space, okay. Now on this vector you can have a lot of vectors which are perpendicular to each other. For example, this is one vector that is perpendicular to this vector, this is another vector that is perpendicular to this vector, this is another vector, this is perpendicular to this vector. So this vector is kind of a pointing outwards actually, okay. And so for example, you can have a lot of vectors that are perpendicular to what you call this given vector actually. Now if you take this vector and you put all of these vectors together, collect them in a in a set, you're going to get, for example, in R3 an orthogonal complement of this vector actually. In other words, for example, in R3 it would be like a plane actually, okay. So take a plane, okay, so take a plane, and on that plane consider this as a normal vector. Then I know that any vector that you draw on this plane is always going to be orthogonal to this given vector actually, okay. And this orthogonal plane is really the orthogonal complement of this given vector. So what do you mean by orthogonal complement? Orthogonal complement of a given vector is really the collection of all those vectors which are orthogonal to it actually, okay. Let me put it in the form of a definition. So here throughout the discussion I'm going to assume that calligraphic V is an inner product space over a field F that could be real numbers or the set of complex numbers. So here's an interesting definition. So it says that assume that you have a subset U of the inner product space V. Okay, so I have a non-empty subset of U that is subset U of the inner product space V. So it's collection of, so it could be one vector, it could be a collection of the vectors. Now, then by U perp, how are we going to read it actually? So we're going to read as U, okay, perp, P-E-R-P. So we're going to read it as U perp. Now U perp is the collection of those vectors from V which are orthogonal to every single vector in U. Okay? Every single vector in U. So what do you mean by an orthogonal complement of U? So collect all those vectors from the inner product space which are orthogonal to every single vector in the vector U, so the set U actually. Okay, so it's a collection of all those vectors. Then this U perp is called the orthogonal complement. Okay, orthogonal complement of U actually. So we will justify this word complementness sooner actually. So from definition, I can say that this U perp is really the collection of those vectors which are orthogonal to every single vector in U. So I can say that U perp is like orthogonal to U. Okay, but what do you mean by complement? I'm gonna write a theorem in a few minutes, which is going to justify this complement word as well actually. So in particular, if this U can be empty set and non-empty set, so if U is a empty set, then the orthogonal perp is going to be the entire vector space, what do you call, V actually. Okay, so if U is empty set, then we're going to say that the orthogonal perp of this vector V is really the entire inner product space. So this is part of our definition. Okay. So let's have some examples of it. For example, take nu to be the space R3 with the Euclidean inner product, with inner product as the dot product. Okay. Then, and take for example vector U as a vector that consists of say 1, 2, 3 actually. Okay, so 1, 2, 3. 1, 2, 3. So it's a single vector that contains only 1, 2, 3. Keep in view that this U is not necessarily a subspace of the V actually. So it's a set which could be empty, which could be singleton, which could be, you know, anything. So the U is this singleton vector, what do you call 1, 2, 3. Then what would be the U perp? U perp of this U, our single vector V, is going to be, I can also call it that it's a perp of the vector 1, 2, 3. Okay, so it's the collection of say vectors V. Okay, it's a collection of say V1, V2, V3, such that the inner product of the 1, 2, 3 with this V1, V2, V3, okay, is equal to 0. Okay, this is what the perp of it. So if you simplify it a bit, so it's the collection of all those points or vectors from R3, which is equal to the product of it. So the dot product of it is going to be V1 plus 2V2 plus 3V3 equal to 0. So all those vectors constitute an orthogonal perp of the vector 1, 2, 3, which satisfy this equation actually. Okay. What would be some exemplary, some examples of, for example, in this space? So indeed 0, 0, 0 is going to belong to the U perp actually. Okay. So it is going to belong to the U perp. Why? Because it satisfies the equation actually. Okay. What could be some other example? Say 1, 1, say negative 1 would also belong to the U perp actually, because this is going to be 1 plus 2 and minus 3, that is going to equal to 0. Okay, so the U perp, so all these are the vectors which are orthogonal to 1, 2, 3 actually. Okay, so the orthogonal perp of a given vector or a given set of vectors is the collection of all those vectors which are orthogonal to the vector V actually. I mean, if you remember from your calculus 3 course or the course that you are doing now, is that you can also treat this equation as the equation of the plane. Okay, so it's the equation of really the plane in which the normal vector is this vector 1, 2, 3. Okay, in which this normal vector is this vector 1, 2, 3 actually. Okay, this will be the equation of the plane with the normal vector 1, 2, 3. So this plane is really the orthogonal perp of this vector 1, 2, 3. Why? Because any vector on this plane is going to be orthonormal to this vector. Any vector or any combination of vector that lies on this plane is going to be orthogonal to this vector. So you're going to say that basically orthogonal perp of a vector is really a plane actually. Okay. Here is another example. Say 7 point another example. Okay, so the example is that consider vector space of, say, matrices actually, okay? So let's, for the sake of simplicity, let's consider what you call M3, where M3 is the collection of the non-singular matrices, 3 by 3 non-singular matrices actually, with the Frobenius norm, okay? With the Frobenius inner product actually, that the inner product xy is y star x actually. If you take two matrices, sorry, A, B, okay, the inner product is B star A actually, the conjugate transpose of B multiplied with A. So this is called what you call the Frobenius norm. Now if you take, for example, U to be the collection of the upper triangular matrices actually. So imagine this U is the collection of upper triangular matrices that goes like this: A, B, C, okay, 0, 0, E, F, and 0, 0, G actually, where these A, B, C, and up to G, they all are real numbers, okay, or maybe the elements from field. Okay, so it's a collection of upper triangular matrix. Now, what would be the collection of, what would be the U perp actually? The U perp on this is going to be the collection of the matrices to which, when you multiply with such kind of a matrix, you're gonna get 0 matrix actually. Okay, so it's gonna be the collection of the matrices. Okay, it's going to be the collection of the matrices. If you multiply those matrices with this matrix or such matrices, you're going to get what you call 0 actually. And what would be those matrices? Those matrices are going to be really matrices of this form, which is going to be 0, 0, 0, and say A, 0, 0, and B, C, 0. So this is strictly lower triangular matrix actually, okay? So this is upper triangular matrix and this is a strictly lower triangular matrix. What do you mean by strictly lower triangular matrix? So a strictly lower triangular matrix is a lower triangular matrix in which the diagonal entries are also 0. This is not a strictly upper triangular matrix because these elements can be non-zero. If these are 0, okay, then you're going to call it that's a strictly upper triangular matrix. But since these can be anything, so you're going to have what you call that these matrices to be the strictly triangular. So it's upper triangular matrix and strictly what do you call upper triangular matrices, strictly lower triangular matrices. So if you take any matrix of this form and multiply with this, okay, so you're gonna say that so this is really, so you're gonna get a 0. So I can say that for this set, the U perp is such kind of matrices actually, and hence you can have other way around as well actually, that okay, if you take the collection of lower triangular matrices, the U perp is going to be equal to the collection of the strictly upper triangular matrices actually. Okay, so that's another example of upper triangular matrices of the orthogonal complement. Now let me prove some very interesting theorem which reveal many different properties, very interesting kind of properties of the orthogonal complements. Okay, and we will also solve a practical problem using what you call orthogonal complements. So let me state the theorem and then prove it. So the theorem goes like this. Theorem goes like this. One is that if say U and V are two subsets of so that U and V are non-empty subsets of the inner product space calligraphic V. Okay. Then you have following. Number one, orthogonal perp of any subset of inner product space is always a subspace of V. Subspace of V and containing 0. And in particular, it contains 0. Okay, 0 vector is always there because 0 is orthogonal to any vector. So for sure 0 is going to be there actually. So no matter what set you have, that set may or may not be a subspace, but the orthogonal complement of a subset of inner product space is always a subspace actually. So that's the first part of it. Okay. So if U is contained in V, okay, so U is a subset of V, then is an interesting thing. Orthogonal perp of V would be contained in the orthogonal perp of U actually. Okay, so if you use a subset of V, the orthogonal complement of V would be the subset of U actually. And this is very much intuitive. For example, you talk about sets, for example. So if I say that this is set A and say this is set B, okay, A is the subset of B. So if you compute the complement of B, so it would be a little set. But if you compute the complement of A, that would be a bigger set actually. So it's intuitively, you have this result. The third property of it is that U perp is basically equal to that if you span the vector U, okay, so consider the span of the set U. We know that the span is always a subspace, and compute its perp. This perp would be equal to the U perp actually. Okay. So in other words, take subset U, consider the span of it, consider all vectors that you can make out of that set U, and consider its perp. That perp would be equal to the U perp actually. Okay. The fourth interesting property is that if U and U perp have anything in common actually, so imagine that their intersection is non-empty, then the only thing that can be common between U and U perp is the 0 vector. Okay, is 0 vector. U and U perp do not necessarily, intersect, because U can be a subset, not necessarily a subspace. But if U intersects with U perp, the only element that their intersection contains is 0. This is another interesting thing. The fifth is, that if 0 belongs to U, set U, then U intersection U perp is still 0. Okay. An interesting fact that what would be the perp of the 0 vector? What would be the perp of 0 vector? Okay. So in other words, what are those vectors which are orthogonal to the entire, which are orthogonal to vector 0? So you're going to say every vector is orthogonal to vector 0. So I would say that this is equal to the entire inner product space. So this is the sixth part. And another interesting property of it is that if you say consider the H of it, H of it, then H is really that if U is a subset of span of U. Okay, so U is always a subset of a span of U, and the span of U is always a subset of U perp of the perp actually. Okay, so if you compute the U perp of the perp, that will contain a span of U, and a span of U obviously contains U actually. Okay, so these are some of the very interesting basic properties of U perp. That U perp is always subspace. If U is the subset of V, then perp of V would be contained in perp of U. U perp, the perp of U and the perp of a span of U both are equal. U and U perp, if they have something in common, that would be 0. If 0 belongs to U, then something that is common in both is going to be 0. And the perp of the 0 vector is entire inner product space. And the U is always contained in the span of U, and the span of U is always contained in the perp of the perp actually. So this is what that I would like to quickly, for example, prove actually. So in order to show that U perp is a subspace, okay, what we need to show that 0 belongs to U perp. And if you take, for example, any two vectors, and if you take any two vectors from U perp, then any linear combination of these two vectors would also be in U perp actually. Okay, this is what is really you need to prove actually. So how can I show it that 0 is in U perp? This is trivial actually, that if you take any vector U from U, then U0 is orthogonal to U, to any vector U actually, for all U in U. Okay, so if you take what do you call any vector U and compute its dot product with 0, you're going to get a 0 for all U. So this is precisely what we mean that 0 is in U perp, because U perp is the collection of those vectors which are orthogonal to every single vector in U. Now, next, say you want to take, say, two vectors from U perp, okay, and I want to show that their linear combination is also in U perp. So what I need to do, let's take, for example, the inner product of this AU plus BV with an arbitrary element of U. Okay, so let W is an arbitrary element of what do you call? W is an arbitrary element of U actually. Then what you can do is that you can, I can break this inner product and I can write this as AUW plus BVW. In fact, I can pull A out of this and you're going to have AUW plus B conjugate VW. Okay? B conjugate VW because or B, what do you call VW? Doesn't matter. Okay, and this is true for all W in U. So what does this mean? This means now I know about U and V that they are also from U perp. So so its inner product with any vector in U is going to be 0. So this is 0, this is 0, so the both are 0. So this shows that this AU plus BV belongs to U perp actually. And hence U perp is a subspace of vector. Now, why the second part is true? Okay. It's important that we must keep, these basic properties of these objects. You will also study in your function analysis course these, structures again, but then the inner product space would be infinite dimensional actually. Okay. Infinite dimension. By the way, this result is true is also when your V is infinite dimensional. Okay. Okay. So let's think about the part 2. So the part 2 says that U is a subset of V and V perp is a subset of U perp actually. So U is subset of V, this is given. And I need to show that V perp is an element in U perp. So let me take say VW, say W from V perp, and I'll show that this is equal to what do you call this will also belongs to U perp. Now what is the meaning of W belongs to V perp? This means that the inner product of V with W is 0 for all V in V. For all V in V actually. So this W is going to be orthogonal to every single vector in V. Okay? But V contains U. V contains U. So if this is 0 for all elements in V, so it must be also 0 for all elements in U, because U is subset of V. So this implies that VW, so this implies that UW would be also equal to 0 for all U in U actually. Okay? So since W is also orthogonal to every single element in U, so this implies that W must be in the U perp. Okay? This must be the U perp actually by definition. So what is the third thing? So you picked an element from here and you showed that it also belongs to here. So this proves the second statement. So what is third actually? Third is that if you can consider the perp of U, it is also going to be the perp of span of U and what do you call and the perp of span of U is contains perp of U actually. So the perp of U and the perp of span of U both are equal. Now using this, I know that U is always present in the span of U. So a span of U is a subspace that is the collection of all those vectors that you can make out of the linear combinations of the element from the elements of U actually. Okay? So the U is always contained in the span of U. Okay? So if the U is contained in always span of U, then by this result, the span of U perp by part 2, span of U perp is contained in U perp. Okay? By 2. So span of U perp is a subset of U perp. So the only thing is now we need to show is the reverse inclusion actually. So I need to show next that why U perp is contained in what do you call a span of U perp. So next, let that V is in what do you call is in U perp actually. So if V is in U perp, this implies that inner product of U with any V with any element from U is equal to 0. The U is equal to 0 actually. Okay. Now consider. So I need to show actually that this V is also an element in span of U perp. So let's take for example an element. So let's take that an element from a span of U. Okay, span of U. So if I pick for example a W from span of U. Okay, span of U, then this W is going to be a linear combination of the element of the vectors from U. So this W is going to be some AI UI vector. I need to show, if I want to prove that V is an element of a span of U perp, I need to show that V is also orthogonal to every single element in the span of U. So I have picked an element from a span of U, and I'll now take the inner product of this arbitrary element with, what do you call V? So if I take the inner product of the arbitrary element from a span of U with